Hello everyone, welcome to another TMLS event, this time in finance, and especially to discuss graphical models for financial time series and portfolio selection. And I just want to remind you, if you didn't till now, please visit the Expo tab to have a chance to win prizes. And also, if you have time, please fill out the profile section. And today we're going to talk about graphical models for financial time series and portfolio selection. I want to introduce our speaker, Jenny. And I also want to mention that if you have any questions, you can put your question in the chat section, and I will ask Jenny at the end of the talk. Jenny is a student at Carnegie Mellon University. Her PhD research is about atomic simulation of liquid alloys and machine learning methods to aid the simulation and their analysis. She has published research on machine learning for finance topics, including graphical models for portfolio selection and modeling bank deposit using bank financial data and macroeconomic variables. She worked at JP Morgan as a quantitative analyst and at Eastman Chemical Company as a chemical engineer. Without further ado, to you, Jenny.
Hi, everyone. Thank you, Beta, for the very nice introduction. Today, I'm talking about graphical models for financial time series and portfolio selection. It is based on a paper of the same title. And our motivation is we want to use graph methods to select portfolios with high return and low risk. And this is a very natural motivation for a lot of investors. It is related to Markowitz portfolio theory. If we have a portfolio, the variance depends on the covariance between the assets. And from a graphical standpoint, a full covariance matrix represents a fully connected graph. And this may not be a good model in reality. We also know that the covariance is likely to change over time. So we want to use graph structures and update them over time. And our approach is to use graphical methods to find structural correlations between assets and then capture the time-varying patterns by updating graphs over time. And we had two main strategies. The first one was latent space or lower dimension space representation of assets. And the second one was clustering and graphical sequences. So I will talk about each of these strategies separately. And we also have a rebalanced simulation backtest to compare our strategy performances.
Jenny, so sorry to disrupt, but it would be great if we can, minimize the screen share notification so audience can see that. Thank you so much. So sorry to interrupt.
Okay. And our data set is the S&P 500 stocks from tech, energy, and finance sectors. And we had daily returns from 2012 to 2019. So our data matrix is like this, and we have the stocks as the rows, and then we have the daily returns as the features on the columns. And we mentioned the latent space representation. So as an example of how this works, if we have a stock and let's say the features are the daily returns for 1 year, so that's 250 daily returns, then we can reduce the dimension from 250 to a smaller dimension, and then the smaller dimension is known as the latent space. So when we reduce the dimension, we want to retain as much information about the original dimension data as we can. And you can think of it as being the structure in the high dimension space. And our questions are, can we learn useful structure in the latent space? And how can we construct portfolios with the information? So there are many different methods to reduce dimension data, and these were the two dimensions that we used. The first one is principal components analysis, or PCA. And in this method and it works well in many cases. And it requires principal components that we will project the data onto. And the principal components are chosen to maximize variance of the projected data onto the lower dimensions. And in our case, we used 3 principal components. And the second method we used was variational autoencoders, or VAE. And this is a probabilistic generative model. So there are 2 conditional probability distributions, Q and P. And Q gives the latent space Z given the data X. And we chose this to be a normal distribution. And then P is a distribution that gives the reconstructed data given the latent space. And we chose 2 different distributions for this. So we actually had 2 variational autoencoders. We used a Cauchy and a normal distribution. And we wanted to try the Cauchy distribution because finance data is known to have fat tails. And we chose our latent space to be 2 dimensions. And Q and P are represented as neural networks. So as an example of how this works, if we have a data point, which is a stock, and its features are the daily returns, that will be the input to the neural network for Q, and the output of the neural network will be the mean and standard deviation for the normal distribution for Q. And then we can sample the distribution to get a latent space representation. And that will be the input to the neural network for P, and the output will be the parameters of either the Cauchy or the normal distribution, and then we can sample that distribution to get a reconstructed data point. And because we are doing sampling of probability distributions, there is this stochastic element. So we did training and simulations for our experiments repeated 10 times. And now we can visualize the latent space. And this is an example of the visualization for the Cauchy autoencoder. And we chose our latent space to be 2 dimensions. So we have the X and the Y axis as our dimensions. And then we're plotting our stocks at their latent space representation. And the 3 colors here are the 3 sectors: tech, energy, and finance. The sectors are pretty separate from each other. So the autoencoder was able to separate the stocks by their sector. And we thought this was pretty remarkable because the only input was the daily returns. So it shows that the autoencoder did learn useful information, and it could also show that daily returns for stocks within a sector are quite correlated. And the Cauchy autoencoder did visualization than the normal autoencoder and PCA. And now that we have a latent space representation, we can use it to select portfolios and then test our portfolio performance. So in our setup, the training data is daily returns for 1 year, and then we do the simulation for the following year. So we have daily returns for 1 year, which is 250 dimensions, and then we can reduce it to a smaller dimension, and then we can reconstruct back to 250. So we can take the difference between the reconstructed data and the original data and take the L2 norm. And this is our measurement of reconstruction error. And these were the portfolios that we compared. There are 10 stocks selected for each portfolio, and there were 3 different selection criterion. So the 10 stocks selected for the portfolio were the 10 stocks with the maximum or the minimum value of that selection criterion. And the first selection criterion was L2 difference or reconstruction error, which is this term. And if a stock has a high reconstruction error, it means that there's a lot of information lost when we transformed it to the latent space. And it could mean that there was some special behavior about the stock that wasn't captured by the latent space. And we also think that maybe if a stock had high reconstruction error, it could mean it had high volatility. So we wanted to use volatility as a selection criterion. And we also used average return over volatility because this is like a Sharpe ratio, and we wanted our portfolios to have high Sharpe ratio. And here I'm showing the visualization for our simulations. So we had our portfolios that we constructed, and now we're using them in the simulation to check the portfolio performance. And here I'm showing the years simulated, 2014 through 2018. And the simulation itself, we started out with 10 stocks in the portfolio, and we distributed it as an equal dollar weight across the 10 stocks. And then every month we buy and sell until we get equal dollar weights across the 10 stocks. So it is a rebalance every month. And here I'm showing the results for the PCA reconstruction error portfolios in the S&P 500. So the max reconstruction error for PCA is the blue line, the min reconstruction error portfolio is the orange line, and then S&P is the green line. And for all of these years that we simulated, we found that the max reconstruction error portfolio for PCA did better than the other 2. And it does have a little bit of a higher volatility, but not too much higher. And then these percentages were the yearly return for the max reconstruction error for PCA portfolio. And here I'm showing the results for some of our results, and the full results were in the paper. So these are the results for the simulation years 2014 through 2018, and the simulation was the equal dollar weight rebalance every month. And for each simulation year, the previous year was used as the training data. And average yearly return here is the average over the 5 simulation years, and then the Sharpe is the Sharpe over the 5 simulation years. So when we look at these results, it shows that PCA and VAE reconstruction error portfolios are able to select high return, low risk portfolios. And the reason is the max reconstruction error, the returns are among the highest out of all of the strategies. And then when we look at each selection criterion, we look at the max and the min portfolio, and we want to compare the 2 because they're the 2 ends of the spectrum. So we want to see a big difference between the 2 of them, and we want to see one of them be better than the other in terms of yearly return and Sharpe. So we see that is the case for the PCA and VAE. The max reconstruction error is better than the min portfolio for returns and Sharpe. But we see that's not the case for volatility. And for average return over volatility, the average yearly return is not as high as the other strategies. So it shows that reconstruction error is an effective way to select stocks that will end up with portfolios with high returns and low risk. And these stocks have some special behavior that's not captured by the volatility or the average return over volatility. And the next part is graphical sequences. This part was done by Zhan. The main idea is that stock correlations change over time, and we want to update the graph so we get an update of the connectivity and the graph structure. And we also know that some stocks will exhibit stronger correlations than others. So we do not want, or we do not need, a fully connected graph. So in this image, we have several things going on. We have the edge connectivities, which are the lines between the stocks, and the darker lines indicate stronger correlations. We also have different colors on the stocks or the nodes, and the different colors represent different cluster assignment. And then we have a 2D embedding, and it's 2D, so we can visualize this. So I will go through each of these items. So we mentioned clustering, and we want to assign our stocks to clusters, and then we can use that to create portfolios. So our clusters are constructed and updated on a quarterly basis using daily returns from the previous quarter. And we use two clustering methods, agglomerative clustering and affinity propagation. And one of the main differences is that agglomerative clustering, we need to provide the number of clusters, and affinity propagation automatically selects a reasonable number of clusters given the data. And in agglomerative clustering, we have each stock starting out in an individual cluster, and then we hierarchically link clusters together based on a linkage criterion. And our criterion was to minimize the sum of squared differences within a cluster. This is known as Ward's minimum variance method. And the output of the method is this, something like this called a dendrogram. And we ended up choosing 15 clusters every quarter. We wanted, because we need to provide the number of clusters, so we wanted to keep it a constant at 15 clusters. And now I'm showing the edge connectivity generation and affinity propagation steps. The first step is PCA to reduce dimensionality, and we get a 2D embedding, and this is also how we did our 2D visualizations. And that is the input to graphical lasso. And graphical lasso gives the edge connectivities. And it also increases sparsity, so we do not have a fully connected graph. And that is the input to affinity propagation, which gives the cluster assignment of the stocks. And affinity propagation changes the number of clusters every quarter. And now we'll talk about how we generated portfolios using the clusters. So for each cluster, if it had more than 10 stocks, we chose the 10 stocks with the minimum distance to the cluster center to enter the portfolio. And if a cluster had fewer than 10 stocks, we did not add any stocks to the portfolio from that cluster. And so we always had at least 10 clusters per quarter, but we only had 3 sectors, tech, energy, and finance. And so because we had more clusters than sectors, it helped the stronger correlations between stocks stand out more. And it also helped us to see the intersector correlations and the intrasector correlations. And another thing to note is that our strategy ended up selecting stocks from the larger clusters more often. And we also had a benchmark method, which was K-means with a fixed number of 10 clusters. And we did static clusters and quarterly updated clusters. And now I'm showing the results for our simulation for the entire time frame. And the simulation was the equal dollar weight rebalance. So we started out with equal dollar weights across the stocks in the portfolio. And then every month we buy and sell until we get equal dollar weight again. And we are showing 4 strategies in the S&P 500. If a strategy says dynamic clusters, it means that we updated the clusters quarterly based on the data from the previous quarter. And looking at the results, the bottom 3 performers were the S&P and the K-means. And in particular, the K-means with the fixed clusters did have the lowest performance overall. And all of the other strategies had the number of clusters changing over time, We updated the clusters quarterly. So we think that updating the clusters definitely helps the strategy performance. And then agglomerative clustering and affinity propagation did seem to do better than the other strategies and the S&P. And affinity propagation did much better than the others. And it didn't have much higher variance than the others. And so affinity propagation was the only strategy that had the number of clusters changing every quarter. And so we think that changing the number of clusters also helps the strategy. So in conclusion, we used graph methods to create portfolios, and we used latent space representation and dynamic clustering and graphical sequences. In the latent space work, we found the latent space does find structural correlations, and using PCA and VAE with reconstruction error can select high return, low risk portfolios. And it has some special behavior stocks that is not captured by volatility or average return. And then for the clustering methods, we found that updating the clusters over time and updating the number of clusters over time helps the strategy performance. So our paper is on archive here if you want to see the details, and thank you for your attention. I'm happy to take questions.
Thank you, Jenny. Thank you for the great and interesting talk. We have a couple of questions. And I want to ask you the first question. In a stock time series, certain extreme point may have much more importance than others. Is there a way to account for these in the latent space?
I think that the reconstruction error is partially accounting for it, because if you have an extreme return, and we are trying to reconstruct the data from the latent space. So if you have an extreme point, then it ends up having a higher reconstruction error, because it might not be able to reconstruct that extreme point from your latent space representation. And I think another thing is that because we used the variational autoencoder and we used the Cauchy distribution, it does possibly, this Cauchy distribution might help it be able to generate those extreme points because it has the fatter tails.
Thank you. Thank you so much. We have a couple of questions about the time frame that you've used in your algorithm. It was, please correct me if I'm wrong, it was from 2014 to 2018. We have a couple of questions. in your perspective, how well will the model work if, for example, we extend the time frame, for example, from 28 to 2020, and if you try to see how this model performed in 2019 and 2020?
Yeah, that's a very good question. So we did do one simulation for 2019 that was actually a forward test, and the simulation did the strategies did well for that 2019, but then we did not try it for other years. Like we didn't try it for 2020. I would say that generally, I think the years that we did look at, most of the years seem to be pretty good markets overall, maybe except for 2018. So, and maybe this drop here. But I think that sometimes the strategy, it could work better in different time frames, because you could think of it as certain time frames, like certain strategies are going to work better, and that's kind of like something that people in finance have found. But I guess like even when we did have this drop in 2018, the max reconstruction error portfolio did perform better than the others. So I think there could be more research to be done about, extending it to more years and doing more simulations.
Great, thank you so much. And there is another question about what is the reason or what is your thought about choosing only 3 industries, financials, energy, and tech, other than reducing the dimensions of the input matrix, including, for example, why not other industries?
I guess like we just kind of just chose these we just chose like S&P 500 stocks because they're like larger, and then we kind of chose these sectors arbitrarily. So I think maybe changing the sectors wouldn't change the results too much if you're still using like the stocks that are in the S&P 500.
Yeah, okay, great. And there are also questions about if you could elaborate more on your proposed approach estimated the value of the index for various years. They've mentioned that if you could elaborate more on slide 7 about the value of the index for various years.
What index is what do they mean by index?
Okay, it would be great, Mohammed, if you can add more explanation for your questions, and we get back to your questions after your, if you elaborate more on that. But in the meanwhile, we also have question on, did you try factor attribution for the selected portfolios, like value, size, momentum? Or including, for example, are you just trading momentum with a 1-year look back at monthly equal weight rebalance?
We did not try that. So another thing that we did try was, instead of doing like an equal weight across the 10 stocks in the portfolio, we did do the optimized weight, where it's solving the quadratic equation using the Markowitz portfolio equation. So that one also has some interesting results that you can see in the paper. But I think we rebalance every month for all of our simulations.
Okay, great. And could you also elaborate on why the max, what is your perspective in that? Why do you think the max difference strategy worked so well Did it identify some extreme stocks that were strong momentum stocks and rode them to higher performance?
We do think that we do think that it identified some like extreme stocks that maybe that stock always had like a average of like a positive return, but those stocks, like some of the stocks that it identified were maybe like in that time period, AMD, it was doing quite well. But it is different from looking at it based on volatility or average return over volatility. So because reconstruction error, if it has high reconstruction error, that means like more information was lost, and it could mean that the stock was very different from like the other stocks in that set. So it had like more extreme values and just like special behavior that's like different from like the other stocks in that set.
Great. We have so many questions. And another question is that do you think network learning algorithms play roles in terms of prediction results?
Network learning algorithms. Which ones are those referring to?
Okay, Howard, if you can provide more explanations, we can again back to these questions. But another question is that for the max difference PCA strategy, again, it refers to slide 7. Are you showing 1 of 10 simulated results, or it is average results?
So for PCA, it's actually every time you solve the PCA in this problem, you will get the same result. So it's going to be the same result every time you solve it, because this is a linear algorithm. So the stochasticity comes in from the variational autoencoder. So those results were averaged over the 10 trials.
Great, thank you. And another question is that, are there other indicators you plan maybe in the future to include in the simulation for forward-looking predictions?
Other things to look at. I mean, I think for our project here, we had a lot of different kind of like experimental setup that could have affected the performance. So like one thing is that we did use that equal dollar weight rebalance every month, and we used like a window of, for this part, we used a window of 1 year as training data and then the next year as simulation. So even changing things like that would affect, could possibly affect performance. And then we do think that looking at how the strategy performs over different time frames, like if you have like an overall good market or overall bad market, we do think that looking more into detail about like how different strategies can perform in different overall environments, that would be something else to look at.
Great. And have you tried, or do you plan to try to plot or do you think it will help to plot the drawdown of different strategies?
I'm actually not familiar with the term drawdown.
Okay. And again, if you can provide more explanation, we can go back to these questions as well. And also, people ask if there is a GitHub link to the work that you did. And another question regarding the code and also the data set is that, I think you've answered that already, but if you can elaborate more on that, is the data set that you've used is open sourced?
Yeah, our data set, we got this using, I think, Yahoo Finance for Python package. So it was a pretty easy to like pull all of the data using that. Unfortunately, we don't have our code on GitHub.
Okay, great.
At this moment, so I guess
amazing.
If that changes, I will update that on the paper website.
Okay, great. And also, Howard, explained more, and he asked that he meant the algorithm to generate the graphical result about the network learning algorithm. He was asked that network learning algorithm play roles in terms of prediction result, and by that he meant the algorithm to generate your graphical result.
Yeah, definitely. So I guess the graphical result, is he talking about like this graph, these graphs here? Okay, so definitely, because the way that these were generated, we had the clusters, and like the clusters were either agglomerative clustering or affinity propagation. And then we did see that affinity propagation did have a much better result versus the other strategies. And affinity propagation is a different algorithm. I guess like in particular, it has a message passing. So if you think about each of the stocks, and you can like I and K, we're trying to get representatives among the data points for each stock. So we want to see what's the best set of representers among the data points that we have. And then it does an iterative message passing between the points. So there are two matrices, responsibility and availability matrix, that represent the messages that each data point is passing to the others. And then when it converges, that means that we have the matrices selecting the best representatives among the data points. And then that's how the clusters are determined. So versus like agglomerative clustering, this is kind of a different method, and K-means is also a different method. But agglomerative clustering is a little bit more similar to K-means, because agglomerative clustering, we were using this Ward's minimum variance method. So in the end, it kind of makes the stocks that are close to each other in the space, but in like a Euclidean distance sense, those will end up being in a cluster. So it's a different method between these two, and I think that's partially why we get a much better result for the affinity propagation. At the same time, changing the number of clusters over time, that probably also helped the affinity propagation.
Great. And one last question is that, did you find any, difference if you tested between equal dollar weighted versus market cap weighted performance?
So we didn't try market cap performance, but we did try like the quadratically solved like optimal risk variance trade-off formula for the Markowitz portfolio theory. And we did see a bit of a difference for that. And actually, when we solved that method, sometimes it ended up allocating all of the portfolio to like one stock. So that might not be like what an investor wants to do. So I think trying something like a market cap weighting, that would probably end up having a different result also. I think it's still, in both cases that we did try, we still saw something like this. We still saw that the max reconstruction error did better than the min for returns and Sharpe for PCA and VAE.
Great. I thought that was the last question, but we have another questions. Could you elaborate on the evaluate performance of the autoencoder architecture that you've used?
Yes, so for the autoencoder, actually the normal and the Cauchy autoencoders both had kind of similar results in our simulations, but the latent space for the Cauchy autoencoder did look better. And then for these neural networks, I think it was like, maybe 1 or 2 hidden layers with like 500 nodes each, something like that. And yeah.
Okay, great. Thank you so much. Thank you, Jenny, for the great and informative talk. And we have a lot of feedback from our audience in the chat section that they've enjoyed the talk. Thank you so much. And thank you all for joining the session and be with us today. Thank you.